This is Module 6 of the Geometric Review and Design, or GRAD, training tutorials. This module is entitled Intersections. In this module, you will understand the different types of intersections and the different elements of a well-designed intersection. Intersection design includes multiple geometric criteria, including horizontal and vertical geometry, islands, turn lanes, sidewalks, curb ramps, and driveways. Intersections are used by multiple users, including vehicles, pedestrians, bicyclists, and transit, and should be designed with all of these modes potentially included in the evaluation. Intersections are defined as the general area where two or more roadways cross or join. These are the areas where most traffic conflicts occur, so it is imperative that good design methodology is followed to ensure good safety performance for all users. Each intersection control has its own geometric characteristics. Stop signs requires everyone to come to a stop, so less stringent design standards can be used as lower approach and departure speeds should be seen. Signalized intersections offer the opportunity for a green light, which means vehicles could very likely negotiate the intersection area at the mainline speed, creating higher approach and departure speeds. Roundabouts offer geometric criteria that force lower approach speeds. Guidance on roundabouts and restricted crossing U-turns has been added to the L&D Volume 1, and FHWA and AASHTO have additional guidance available for alternative intersections. Choosing the right intersection control is important and sometimes tricky, as multiple factors must be considered, including left turn capacity, through capacity, pedestrian usage, and geometric characteristics. FHWA has tools to assist designers with this task. Intersection Control Evaluation, or ICE, is a data-driven, performance-based framework and approach used to objectively screen alternatives and identify an optimal geometric and control solution for an intersection. The Safety Performance for Intersection Control Evaluation, or SPICE, performs an HSM-based predictive safety analysis of at-grade intersection alternatives and ramp terminal intersections and is intended for planning level safety analysis. The Capacity Analysis for Planning of Junction Tools, or CAPX, is used to evaluate selected types of innovative junction designs, including 8 intersections, 5 interchanges, 3 roundabouts, and 2 mini-roundabouts using given peak flow volumes. Design and operational guidance on roundabouts shown in the top right and restricted crossing U-turns, or R-cuts, shown in the bottom right, has been recently added to the L&D Volume 1, and FHWA and AASHTO have additional guidance available for alternative intersections. These 2 intersection controls will not be discussed in this module. Look for a future module on these topics. The recommended intersection angle is between 70 and 90 degrees. 60 degrees can be used if the intersection is signalized or if it is skewed so that the driver on the minor roadway has the acute angle on their left side. Let's use a real-world intersection to demonstrate what it means to have the acute angle on the driver's left side and show the best situation from a geometry perspective to allow a right turn on red. The image on the left shows the acute angle on the driver's right side. This angle forces a driver to turn a large degree to see an approaching vehicle. Their own vehicle can block the sight line due to the size of their windows. Finally, this movement can be especially difficult for older drivers who may have experienced a decline in their head or neck mobility. Right turns on red may not be appropriate to permit at this location. The image on the right shows the acute angle on the driver's left side. This is a much better visual angle for drivers who are looking at approach vehicles to find gaps and turn right on red. For this, right turns on red may be permitted. NCHRP Report 600, Human Factors Guidelines for Road Systems, goes into detail about this angle concern. Figure 202-1 shows the maximum centerline deflection without a horizontal curve and is used primarily for signalized intersections where the through movement could travel through the intersection at a green traffic light at a higher speed. Skewed intersections create challenges by reducing sight distances and causing drivers to have to turn their head and necks in awkward positions to see along the intersecting roadway. Figure 401-1 shows a strategy of realigning the crossroad to eliminate or reduce an existing heavily skewed intersection using a series of reverse curve combinations. Tangents are provided between curves to transition the super elevation rate and adjacent to the through road to transition the cross slope of the crossroad to match the profile grade of the through road. Here's an example of an existing high-speed rural skewed intersection. The left image is the existing intersection where the heavy skew angle and the vertical profile on the west and north legs have created deficient sight distances and unsafe conditions. The image on the right is one way to overcome skewed intersections by using a roundabout. The improved geometry for the approaches coupled with the slower speeds made this solution a viable alternative to improving the safety deficiency at this location. The left image is another example of a roundabout being used to improve the horizontal deflection through an intersection effectively. Without this intersection treatment, the northbound and southbound through lanes would have to deflect significantly through the intersection. The southbound movement could potentially conflict with the northbound movements if the driver didn't turn sharp enough to follow the intersection alignment. The roundabout eliminates this concern. The right image is an example project that has a significant horizontal alignment concern for the eastbound and westbound through movements. Typical improvements, including realigning the approaches or implementing a roundabout, were shown to not be feasible from a cost and an impacts perspective. The crash history was reviewed and determined that there was not a safety concern due to the intersection geometry, so the existing configuration was left in place. As with every project, reviewing the crash history and purpose and need is essential to determine what improvements should be made. Let's look at an example of a horizontal deflection through an intersection. The image on the left was a first proposed design in downtown Cleveland at East 9th Street and Carnegie Avenue. Notice the deflection of the two inside through movements showed in blue. The southbound inside through movement must shift east almost an entire lane width, which could easily create path overlap problems with the adjacent through lane in the event they both attempt to enter the middle through lane south of the intersection. The northbound through lane must shift nearly half a lane to the east. This could create a potential conflict with the opposing left-turning traffic. The image on the right is that same intersection with some striping changes applied to improve the horizontal deflections. Note the striped out pavement on the south side of the intersection opposite the left turn lane to better align the through movements. This reduces the path overlap conflicts that were originally present. This module will spend a lot of time discussing the intersection, but the approach to the intersection, known as the intersection area that is within 60 feet of the mainline edge of travelway, requires good engineering design because often vehicles are coming to stops or slowing down and use this area to also see the entire intersection area. The intersection area provides the vertical transition from the through road and the crossroad, and care should be given to ensure that transition is as smooth as possible given the intersection control. Figure 401-2 shows the profile design for a crossroad interacting with the normal crown through road using a stop-controlled intersection. For these intersections, it is expected that the traffic will fully come to a stop on the crossroad, so the concern of the vehicle bottoming out or having to maintain a high rate of speed is minimal. As a result, the transition between the through road and the crossroad profile can be more abrupt using a short vertical curve and vertical grades that can be as great as 5% up or down. Once outside the intersection area, grades and vertical curves along the crossroad are controlled by the design speed of the crossroad, which a designer should refer to Section 203 for guidance on how to accommodate an acceptable design speed. Figure 401-3 shows the profile design for a crossroad interacting with the super elevated through road using a stop-controlled intersection. This shows the same intersection area width of 60 feet and establishes criteria for vertical curve lengths and vertical deflections depending on which side of the super elevated roadway the profile is located. Once outside the intersection area, grades and vertical curves along the crossroad are controlled by the design speed of the crossroad, which a designer should refer to Section 203 for guidance on how to accommodate an acceptable design speed. Figure 401.4 establishes how a profile should be developed along the crossroad when the intersection is signalized. The difference between a signalized intersection and a stop-controlled intersection is that at a signalized intersection, there's a possibility that the traffic light is green and the traffic can travel through the intersection along the crossroad without slowing down. As such, the profile should be established to meet the design speed of the crossroad. Notice in example C at the bottom of figure 401-4, rounding is established across the mainline road extending from the edge of pavement to edge of pavement along the mainline road. This is to minimize the 3.2% vertical deflection that would exist along the crossroad profile through the intersection if traversing the crown line, assuming a normal crown cross slope of negative 1.6% extending on each side from the crown line. Here's an example of the crossroad profile, in this case commercial road, being adjusted to match the cross slope of the primary road, in this case East 9th Street, shown in the profile image with a blue box. In this case, East 9th Street is along a flat horizontal curve that allows the cross slope to remain at minus 1.6% or normal crown through this intersection. However, notice that the intersection is not perpendicular, and the skew angle along with the profile of East 9th Street define the cross slope of East 9th to be minus 2.59% along Commercial Road through the intersection. The identification of this tie-in cross slope for the profile of Commercial Road was done by creating a proposed surface at the intersection, then draping the baseline of Commercial Road on the surface to get the takeoff grade. Combinations of pavement cross slopes and profile grades may produce unacceptable edge of travel way profiles within the intersection. For this reason, edge of traveled way profiles should be plotted and graphically graded to provide a smooth profile. For the example project, on the right side, strike a line across the west leg of the intersection at elevation 816.98, shown as a green line, until it intersects the northwest quadrant radius return at elevation 817.39. Do the same thing on the north leg of the intersection at elevation 818.14, shown as a blue line, until it intersects the northwest quadrant radius return at elevation 817.90. Attempt to straight grade between those 2 points, then continue those grades around the rest of the radius return. Then check the pavement cross slopes. Iterate as necessary to get positive drainage without excessive cross slopes. Notice in the northwest quadrant, everything drains to the west. Notice in the northeast quadrant, a low point had to be created along the radius return, and a drainage structure was placed there to allow the radius return to drain to it. This image shows an example of a 3-center curve using 150-foot, 50-foot, and 150-foot radii curves for the approach radii. The approximate equivalent simple curve radius is 60 feet, but the 3-centered curve layout yields a slightly tighter footprint. This layout is appropriate for a single unit truck and a passenger car. With all approach radii designs, truck turning software should be applied to check that the footprint accommodates your design vehicle. In urban settings, while speeds are typically lower than rural conditions, right-of-way is often very constrained. Often the roadways are wider with more lanes and there are pedestrians to account for. For these reasons, designers should balance the needs for many users and develop approach radii sensitive to the context of the area and able to accommodate all users. When designing urban approach radii, use sound engineering judgment. Larger corner radii result in longer crossings at intersections for pedestrians. Determine the likelihood of specific design vehicles that may have been used to specify the larger corner radii at these intersections and whether the design should be developed for a smaller vehicle if it is more prevalent. Figure 401-4A offers guidance on how to transition between curbed approaches and uncurbed main lines. Extend the mainline uncurbed paved shoulder parallel to the mainline centerline until it intersects the approach curb and gutter and transition the height of the curb using section 305.4 to avoid a vertical snag point. Figure 401-4B offers guidance on how to transition between uncurbed approaches and curbed main lines. 2 options are available. Option 1 is to extend the curb around the radius return and transition the change in width over the radius return. Option 2 wraps the uncurbed paved shoulder around the intersection radius until it is tangent to the main line and transition the change in width using a 4-to-1 taper rate prior to the radius return. Transition the height of the curb using section 305.4 to avoid a vertical snag point. Section 401.6 discusses the options for approach lanes at intersections. These include left turn lanes, dual left turn lanes, right turn lanes, dual right turn lanes, and two-way left turn lanes. Let's begin with left turn lanes. Sight distance is important for drivers to identify acceptable gaps in opposing traffic when executing a left turn maneuver. Opposing left turn lanes should typically be aligned directly across from one another. When developing left turn lanes, there are several ways to do it, but designers need to understand the potential work limits and impacts with each. To develop a left turn lane along a roadway that has no median, the through lanes must be tapered away from each other by widening the pavement with enough width to place a left turn in between them. This can be done by widening the pavement using half of the necessary left turn lane width on each side. This will require a shorter taper length than the option that widens the pavement the full left turn lane width on one side only. For roadways with medians, opening the left turn lane within the median is logical. For roadways with wide medians, offset left turn lanes are typically utilized to align the opposing left turn lanes with each other. Figure 401-7 shows how to develop the left turn lanes. When determining the approach taper, which is the taper used to shift the through traffic to the right, determine whether your roadway is a high-speed or low-speed facility and use the correct taper equation. The departure taper, which is the taper used to shift the through traffic to the left, should taper using the same taper rates using W times S or W times S squared over 60, depending on the speed of your facility. The diverging taper, the taper used to fully develop the left turn lane, should normally be 50 feet. Figure 401-8 includes a table to determine the deceleration length for a given speed. Because the deceleration length is adjacent to the storage length, and there is a possibility that a vehicle could be stopped at the edge of the storage length at the back of the queue, the deceleration length is primarily the stopping sight distance for the given speeds. Note that the diverging taper length is included in the deceleration length. Figures 401-9 and 401-10 are to be used to calculate the storage length, which is the number of vehicles that are expected to get through a single traffic signal cycle based on the traffic volume using the left turn lane and the number of traffic signals cycles per hour. Good practice is to set the location of the stop bar first using truck turning templates to avoid conflicts with adjacent turning vehicles from the other approaches in the intersection, then finalize the turn lane placement. Evaluate the storage length that can be provided to see if the adjacent through lane's storage length is too short and is blocking the left turn lanes and not allowing them to be fully utilized, or if the left turn lane storage length provided is too short and is blocking out the through lane. The width of the right turn lane should be consistent with the normal width of the facility, but additional width may be warranted on roadways with curbed median sections to account for drainage spread. Offset left turn lanes should be used on facilities with wide medians to align the opposing left turns and provide adequate sight distance. Figure 401-8 shows how to shift the left turn lane away from the adjacent through lanes in stages. Notice that the deceleration length includes the diverging taper length and that the 8-to-1 taper to offset the left turn lane is included in the storage length. The minimum storage length should be 50 feet, which is about the length of two cars. The image on the left shows an intersection that utilizes the offset left turn lane guidance showed in Figure 401-8 to the right and illustrates how the two opposing left turn lanes are now aligned with each other. Aligning the opposing left turn lanes provides zero offset and is common on facilities that have narrow or no medians. For roadways with wide medians, designers should attempt to achieve positive offset of the left turn lanes like in the image in the top right, which is when there is some buffer between the left turn lane and the through lane in the same direction. This allows the turning vehicles to be left of center of the opposing turning vehicle, allowing them to have adequate sight distance to find gaps in the opposing traffic to turn within. Positive offset also helps ensure that there is no path overlap between the opposing turning vehicles. Negative offset is when turning vehicles are right of center such as the image in the bottom right, not allowing them to see around the opposing vehicle or see far enough past the vehicle to find an acceptable gap in the opposing through traffic to turn within. Signalized intersections with negative offset turn lanes should use a protected left turn signal phase, which requires an additional signal phase in the cycle length. The overall path of the vehicle through the intersection, measured from the stop bar to the point where it is through the left turn and clear of the opposing through traffic, is long and will require sufficient clearance interval. These two items make the signal timing needed to accommodate the negative offset left turn lanes more inefficient than the positive offset left turn lanes. For the positive offset turn lanes, because the turning vehicles should be able to see past the opposing left turn traffic and find acceptable gaps, permissive left turn signal phase can be provided, which would not require an additional signal phase in the cycle length. The clearance interval will be shorter too, because the distance from the stop bar to the point where the vehicle clears the opposing through movement is shorter. Determine the appropriate design vehicles for dual turns. Depending on the location, it is very common to use a WB62 truck for the outside lane and a single unit truck for the inside lane, but this can vary. Review common vehicles that would be making the turn. For the capacity analysis, dual left turn lanes require a dedicated signal phase, which can reduce the efficiency of the signal operation. Check the geometry of the turning vehicle paths to ensure there is no path overlap through the turning maneuver. Figure 401-12 shows how to develop dual left turn lanes. This figure highlights two different deceleration lengths for a given design speed because it is assumed that the vehicle would be using L2's deceleration length, would already have been slowing down, and wouldn't be starting at the design speed value. Also note that the right-hand left turn lane should be aligned with the single left turn lane if only one left turn lane is present on the opposite approach. Right turn lanes are utilized to get right turning traffic out of the through lane and minimize the impacts of them slowing down to make the turn on the overall speed of the through lane. The width of the right turn lane should be consistent with the normal width of the facility, but additional width may be warranted in curb sections to account for drainage spread. Dual right turn lanes can be used at the end of a ramp terminal when a heavy right turn is present and there is a desire to minimize the queue when you have limited length of the ramp before it gets onto the main line. Another opportunity to use these is when a single right turn lane is over capacity. In these situations, the first step would likely be to see if the right turn on red can be permitted. If it can, and it still leaves the right turn over capacity, then a dual right turn lane could be implemented, recognizing that only the outside lane would allow the right turn on red, and drivers would want to utilize the outside lane nearly exclusively. The inside right turn lane could offer enough utilization to allow the right turn to function acceptably. For every situation where a right turn on red is permitted, designers should evaluate the traffic operations on the main road, especially if there's a downstream left turn lane. Allowing right turns on red can establish a weave along the main road if they are attempting to turn right at the intersection, then left at the next intersection along the main road. Figure 401-11 in the L&D Volume 1 provides guidance on the inside radius of turning movements to create the expanded throat width you see in this image, highlighted by the blue arrow in the image. Section 401.6 discusses turn lane warrants that should be completed to determine if they are needed. Often designers default to adding these to projects, but sometimes they aren't necessary if the turning volume or the opposing volumes are a low percentage of the approach volume. They should be checked for all projects and added to the project file. Figures 401-5 are the left turn warrants, and figures 401-6 are the right turn warrants. Ensure you are using the correct figure in the L&D manual based on urban versus rural and the number of lanes on the highway. Two-way left turn lanes are good options for getting left turning traffic out of the through lanes. These can be used to improve the capacity of the through lanes while maximizing safety by allowing decelerating vehicles to vacate the faster through lanes. Avoid extra wide two-way left turn lanes. Anything greater than 14 feet wide can encourage side-by-side operations in the single lane. Using truck turning templates, designers should position stop bars on adjacent turning movements so that the left turning vehicle can make the turn without encroaching on the adjacent lanes of traffic. One of these stop bars that should be evaluated is shown with the blue arrow in this image. When these adjacent lanes are turn lanes, the impacts on the available storage lengths should be determined, and potentially the signal operations such as cycle length, phase length, and clearance interval should be optimized to account for the larger intersections or revised storage lengths. Geometrically, provide 2-foot clearance between edge of shoulder or traveled way and closest tire path. Sometimes it is appropriate to use adjacent lanes on the approach or departure side of the intersection to accommodate a specific design vehicle to minimize the intersection footprint. Similarly, encroachments into the opposing lanes may be acceptable. These scenarios should be reviewed by the designer and coordinated with Office of Roadway Engineering using the scenarios shown in this image. In any case, it is very important to identify the most appropriate design vehicles for the intersection design. The L&D Volume 1 details the recommended intersection design and check vehicles for various roadway classifications and identifies opportunities to justify a smaller vehicle than what is in the table if appropriate. Here's an example of what to watch for when establishing the stop bar locations. Notice the southbound to eastbound dual left turn movement in this image. This was designed using a WB62 truck on the outside with a single unit truck on the inside. Notice how staggered the southbound left turn lane's stop bar is relative to the through right stop bar. This wasn't done because of the eastbound to northbound left turn lane like would normally be, but rather because the southbound to eastbound left turn lane had to access the receiving lanes on the east leg of the intersection. Shifting the southbound to eastbound left turn lane's stop bar to the south would not have allowed the turning vehicles to access their targeted receiving lanes and would have substantially increased the size of the intersection. All movements should be analyzed not just for geometrics, but also for intersection capacity, because in this example, the intersection area became large, creating a need for a longer clearance interval for the turns to complete their movements. Figure 401-11 in the L&D Volume 1 provides a guidance on the inside radius of turning movements to create the expanded throat width you see in this image, indicated by the blue arrow. This expanded throat width, or increase in the width of the turn lane through the turning maneuver, is used to accommodate vehicle tracking and reduce adjacent vehicle conflicts. Islands serve 3 primary functions. 1, to control and direct traffic movement. 2, to divide opposing or same direction traffic streams. And 3, to provide refuge for pedestrians. Most islands combine functions. This image shows multiple examples of common island types. The blue arrow is pointing to a curved median island that is used to separate the left turn lanes from the opposing through movement. This median island also forces the driveway access to the left to be right in, right out. The green arrow is pointing to a curved pork chop that defines and enforces a right in, right out access. It is important to remember that intersections should not be barriers for the other users in the corridor. Curb return size impacts vehicular turning and pedestrian crossing movements. There are 2 distinct radii at an intersection: the effective turning radius of a selected design vehicle and the radius of the street corner. When the radius of the street corner is designed to solely accommodate the effective radius or the vehicular turning movement, the radius size can be large, creating longer crossing lengths for pedestrians, increased exposure time to vehicles, and higher vehicular speeds. To better accommodate all transportation modes, a best practice is to design a tighter radius return and minimize the effective turning radius. This can be achieved by setting the curb return radius using the smallest design vehicle possible. Provide flexibility in which lane a vehicle can turn into, typically not the curb lane. Restricting right turns on red to remove the expectation that a vehicle must turn into the curb lane, and to accommodate trucks and buses on designated routes. Pedestrian visibility at an intersection is critical to pedestrian safety and the vehicle-pedestrian interaction. The proximity of parking to a curb return can reduce or eliminate the visibility of a pedestrian entering a crosswalk to an approaching motorist. Ensuring parking is a minimum of 20 feet away from the crossing location on roadways with speeds 25 miles per hour or less, and 30 feet away from the crossing location on roadways with speeds between 26 and 30 miles per hour can increase pedestrian visibility at an intersection. Where a parking lane is present adjacent to a curb extension can be considered to move pedestrians away from the sidewalk and further into the field of vision for motorists before the pedestrian enters the crosswalk, as well as shorten the crossing length. The extension is typically extended out to the edge of the parking lane. Section 306.3 of the L&D Volume 1 discusses curb ramps. A curb ramp is composed of a landing or turning space, a ramp, and flares of some width. In general, curb ramps should have 2% maximum cross slope, shown by the green arrow in the image, and all surfaces should not exceed a 1/4 inch vertical offset at joints. A minimum 4 foot by 4 foot landing should be provided, and a 5 foot by 5 foot landing is preferred unless the landing is constrained on 2 or more slides. Then the 5 foot by 5 foot landing is required. A 2% maximum landing cross slope, shown by the blue arrow in the image, is required. The ramp portion shall have an 8.33% maximum running slope, shown by the black arrow in the image, and should not exceed 15 feet in length when chasing grade. The running slope should not be flatter than 5%. Curb ramps are required to have a detectable warning mat. These mats alert visually impaired pedestrians that they are leaving a pedestrian facility and entering a roadway. The detectable warning surfaces shall be placed per the ADA guidelines or ODOT standard construction drawings and be a contrasting surface color. Note that a sidewalk that is flush with a roadway surface does still require a detectable warning. These are the different types of curb ramps that can be implemented. Perpendicular ramps are installed perpendicular to the pedestrian path and typically used with 10-foot wide sidewalks or where a tree lawn is between the curb and sidewalk. Parallel ramps are oriented parallel to a pedestrian's path. These ramps are typically placed where the sidewalk width is less than 10 feet and a perpendicular ramp is not feasible. Blended transitions should only be used where major impacts to the surrounding infrastructure or right-of-way are a concern with traditional ramps. The blended transition ramp is typically centered on the radius returns to provide access to multiple adjacent corner radii. Consider increasing the ramp width to increase accessibility and require less maneuverability to align with the ramp. Single-sided parallel ramps are placed on radius returns where the wall continues straight through the intersection and does not curve around the radius return to continue along the side street. Check the height of your curb if you're retrofitting curb ramps into an existing corridor. A curb height that is taller or shorter than the standard 6 inches will influence the length of the ramp to meet the ProWAG requirements for slope. While not an ADA requirement, ramp alignment can influence the ease of use for pedestrians with disabilities. The alignment of the ramp pair should provide as direct or straight a path as possible, minimizing complex maneuvers for pedestrians that are mobility challenged. An optimized alignment is illustrated with the green arrow, while the red arrows illustrate a less than optimal ramp alignment. Location of the curb ramp along the radius return is important for pedestrian visibility. It is preferred that curb ramps be placed close to or within the radius return to increase pedestrian visibility for motorists. Curb ramps that are further away from the radius return result in ramps that are located further away from an intersection and out of the line of sight for turning vehicles. The ramp alignment and location should be carefully reviewed to identify an optimal crossing location. Location of pedestrian push-button facilities can also influence curb ramp locations. There are specific design requirements that must be met for ADA compliance. It is important to work closely with traffic designers to coordinate the location of the curb ramp relative to pedestrian push buttons. Curb ramp design can require innovative thinking. The location shown on the left side has an existing radius return that is so large there isn't enough room for a second curb ramp to facilitate crossing the north leg of the intersection. Developing a smaller radius return, as shown on the right side, allows more room to be created for an additional ramp. Another example could be locations where existing site constraints do not permit the straightforward construction of a single ramp type. For instance, steep roadway grades can make a perpendicular ramp difficult to design and meet ADA requirements. Using a combination of a parallel ramp and perpendicular ramp to manipulate the slopes and achieve compliant grading may be necessary. Similarly, projects with curb ramp retrofits and minimal pavement reconstruction could require a small amount of full-depth pavement reconstruction adjacent to the curb ramp to ensure ADA-compliant grades can be achieved. Another key component to intersection, radius return, and curb ramp design is ensuring positive flow for stormwater runoff. While detailing the elevations of the radius return and curb ramps on intersection details, it is important to assess how the drainage flows through the intersection. It is critical to ensure positive drainage to adjacent storm structures is provided to avoid ponding or trapping of debris in the curb ramp, like what is highlighted by the blue arrow here. It is possible to warp the pavement around the radius return to achieve positive drainage. This warping can push the drainage flow entirely around the radius return or can create high or low points to move water in specific directions. When identifying drainage patterns and placing basins in low point, be sure to avoid placing a low point within a radius return on a small radius. Catch basin castings do not curve and cannot be placed within smaller corner radii. Some intersections include median islands within the roadway. These islands provide a divider between traffic lanes and can serve as a refuge for pedestrians crossing the roadway. The minimum width of the face of curb to face of curb measurement of a median should be 6 feet. Where bicycles, wheelchairs, scooters, or large groups of pedestrians are expected, or on high-speed roadways, a minimum median width of 8 feet is preferred. The minimum pedestrian access route width should be 5 feet. If used as a pedestrian refuge, detectable warnings should be placed at the edges of the median. In intersections with long crossing links, confirm the amount of time a pedestrian requires to cross the roadway. If the necessary crossing time negatively impacts overall intersection operations, it may be necessary to create a 2-stage pedestrian crossing requiring a pedestrian push button within the median. Section 800 in the L&D Volume 1 discusses driveway design. These are included in this module because of the interaction with the roadway at what amounts to another intersection. Section 803.2 discusses rural residential drives and field drives. These should normally conform to Type 1 design as shown in Standard Construction Drawing BP-4.1 using circular radius returns rather than the chamfered returns. Similar to designing roadway intersections, avoid high skew angles with driveways. Ensure that driveways are wide enough to accommodate a single vehicle turning in or out of it effectively, and the minimum width should be 12 feet. Driveway spacing should be analyzed to determine if there is a safety or operational concern. Combining access or access management strategies may be necessary to maintain acceptable safety performance on the roadway. Information can be found in the State Highway Access Management Manual. Section 804.1 in the L&D Volume 1 provides guidance for driveway profiles on uncurbed roadways. These are assumed to be along roadways without sidewalk or tree lawns, so the drive profiles are intended to provide a gradual transition from the roadway to the driveway vertical alignment. This means using vertical curves placed outside the graded shoulder width to transition grades and avoid maximum grades exceeding 10%, 8% maximum grade are preferred. Either Type 1 or Type 2 drives shown in Standard Construction Drawing BP-4.1 may be used in urban residential areas. Type 1 drives utilize circular radius returns like what is common for typical roadway intersections. Type 2 drives utilize chamfered radius returns. Curbs shall not extend closer to the main line edge of travel way than 8 feet or the treated shoulder width, whichever is greater to avoid curb obstruction for vehicles such as snowplows using the shoulder. The curb adjacent to the driveway should be transitioned in height per Section 305.4.1. Section 804.2 in the L&D Volume 1 provides guidance for residential driveway profiles on curbed roadways. These often have sidewalk or tree lawns adjacent to the roadways, and these create additional profile requirements because of the potential interaction with pedestrians and other users. Figure 803-3 provides guidance on driveway widths, profile grades, and running slopes for urban residential drive details considering the tree lawn and sidewalks. The presence of a tree lawn forces the driveway's vertical grade to increase to meet the sidewalk elevation, which is typically vertically above the gutter elevation by the height of the curb. Without the tree lawn, a parallel ramp is placed in the sidewalk approaching the drive to lower the sidewalk to one that is closer to the gutter elevation. Outside of the traditional intersection area, the intersection of pedestrian facilities and driveway also has important design considerations. For residential drives, try to avoid the roller coaster effect, the result of a sidewalk dipping vertically up and down to cross driveways. Keep the sidewalk at a consistent elevation behind the curb and tree lawn and adjust the driveway apron to meet the proposed walk or shared use path. No detectable warnings are necessary at these drive crossings. The access requirements for most commercial developments can be served by driveways having standard design characteristics. The exceptions are driveways having high traffic volumes, those being used by large vehicles, or those serving businesses which have traffic patterns unique to the business being conducted. Figure 803-8 provides guidance for commercial drives, both along uncurbed and curbed roadways. Figure 804-1, shown here, provides profile guidance for commercial driveways along curbed roadways. This guidance helps develop profiles that are compatible with sidewalks that maintain good accessibility for those using the sidewalk. Designers should check to ensure that the designed vehicle doesn't bottom out, especially when sidewalk is present or along a crest-shaped profile. At commercial drives, or when the walk is at the back of the curb, it may be necessary to introduce curb ramps along the walk to transition the walk down to meet the drive apron. Use engineering judgment when determining the need for this. Sometimes the drive apron is adjusted to meet the sidewalk and ramps are not provided. Detectable warning mats are typically not provided but may be placed where drives experience a high volume of traffic. Determine vehicle usage before placing mats. This module discussed several terms associated with intersection design shown here. Intersections are the locations that offer the most conflicts between multiple users. As a result, to maximize the safety and operations of the intersection area, good engineering practices such as maximizing sight distance, improve sight lines around turning vehicles, and avoid path overlap between adjacent and opposing turning vehicles need to be utilized when designing intersections. Driveways were included in this module because they should be designed as minor intersections because they offer the same potential conflicting turning movements and challenges that intersection design offers. This module should have provided you with the understanding of how to design intersections that achieve proper sight distances and adequate space for vehicles to make their turning maneuvers.